then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings, calculus students. Welcome to lesson 12. Let's go. Okay, this lesson is mainly about the squeeze theorem, also sometimes called the sandwich theorem or the pinch theorem. When we get into it and look at it from a graphical perspective, you'll understand why. This is a theorem that is used to solve pretty difficult limits that we couldn't solve in traditional means, and we can use this theorem to solve some pretty hard to reach limits. Let's look at today's agenda. So on today's agenda, we're first going to look at some harder limits. Now, I said harder limits. I didn't say hard limits, but limits which are, harder than what we've been doing. And these are limits that we're going to solve algebraically. So not graphically, or numerically, but algebraically. So they're a little bit harder than what we've been seeing, and are also a little bit harder than the type of limits that you would typically see on an AP exam. So these limits are a little bit harder. And these are more like limits you see in a traditional college calculus class, these type of limits. So, albeit they may be a little bit harder than what you may see on an AP exam, there's still limits that are good to understand how to solve, and the algebra involved in solving them is very useful material. So then we're going to look at two special limits. And then it says the squeeze theorem, and it's really not necessarily in that order, because the two special limits, one I'm going to look at before the squeeze theorem, and the other one I'm going to find using the squeeze theorem. So those two things are kind of a little bit intermixed, but we're going to look at these two special limits. So when I go over the two special limits, these are limits that you want to study. So these two limits are limits you want to have memorized, because they're going to come up. They're going to come up pretty important when we start doing derivatives. These two limits are going to play a pretty important role for a couple derivatives that we're going to do. So let's go ahead and take a look at these harder limits. So what I'm going to do, I'm just going to work through some examples and kind of explain the methods I use to solve these particular limits. Once you get accustomed to these methods when seeing these type of problems, you'll be able to solve them fairly easily, I believe. But at first, most of these techniques are probably going to seem new to you, but let's go ahead and take a look. Okay, so here's the first limit I would like to solve, and as you can see, it says the limit as x goes to 0 of the square root of x plus 1 minus x over x. Now, what we normally do when we're solving limits like this algebraically is of course the same thing. We like to plug in the number for x and see if we get an answer. If we get an answer, and that answer is going to be our answer. Of course, we know this is not going to work, because, if I plug it in 0, it will give me an answer. What would be the fun of doing this example? But I'm going to go through the routine nonetheless. So if I plug in 0 for x here, that would be 0 plus 1, which is 1. The square root of 1 is 1. 1 minus 1 is 0. 0 on top, and obviously 0 on bottom. So this gives me the indeterminate form of 0 over 0. So there's an indication that there's hope there. Now, the question is, what type of hope do we have? So previously, type of guys we were doing, we looked at ways to factor. And believe it or not, I actually could factor this numerator. I don't want to. There is a way to factor this. In fact, one of the examples I'm doing here of these harder limits, you'll understand what I mean by there's a way to factor this. But I'm not going to factor this. What we do in a lot of cases like this is we like to rationalize the radical. So you're probably familiar with rationalizing the denominator, where you don't want a radical in your denominator on many things that they cover in pre-cal and algebra 2. Here, it really doesn't matter if it's our denominator or numerator. When we see a radical, we like to rationalize it. Now we're going to rationalize it based off of the following property. I'm going to use a random paper to explain this property. You all know, and the property is that a plus b times a minus b is a squared minus b squared. So that's a property you're all familiar with. Now, the good thing about this particular property is the result are two things being squared. So if one of these items has a square root, I get rid of the square root because the result is things being squared. So, and before I go, notice the property here is just you take one thing times the exact same thing, but with a minus sign instead of a plus sign. That's how you get this phenomenon. So if you notice here, I have the square root of x plus 1 minus 1. So if I was so bold to multiply this by the square root of x plus 1 plus 1, and then I'll get that a squared minus b squared phenomenon. Now, of course, what I do to the top, I have to do to the bottom to maintain equality. So put the same thing on the top, on the bottom, square root of x plus 1 plus 1. And again, why we do it to the top and the bottom is because something over itself is 1. So if I'm doing it to the top and the bottom, I'm not changing the value of this. I'm really just multiplying it by 1, but it allows me to represent the expression differently, which may be of a benefit to me in finding this particular limit. So let's go ahead and multiply the top. Again, what I'm going to get is this guy squared minus that guy squared. So this guy squared is x plus 1. And that guy squared is 1, so that's x plus 1 minus 1. At the bottom, there's no need really to multiply it out. Keep the x there. So x times the square root of x plus 1 plus 1. Distributing that x to this is not going to do anything. Now, look at what happens in the numerator. 1 minus 1 cancels. Now, also understand what's causing the problem in this original problem. The issue is, albeit we got 0 over 0, the real issue was 0 in the denominator. So the problem, because I got to plug in 0 for x, the problem with the expression is this x that's down here. So if you notice up here in this numerator, 1 minus 1 is 0, I'm just going to be left with an x up here. And then you have an x there, and then you have this guy square root of x plus 1 plus 1. And so now I can cancel this x down here, which was causing all the problems. So that x will take care of that x. Now understand, when something canceled, you're left with 1. Some people sometimes mistakenly think you're left with 0. You're not left with 0, you're left with 1, because essentially what I'm doing is dividing x by x, which of course is 1. So now I have an expression that I can plug in 0 for x and it won't make my denominator 0. So I'm in good shape. So I'm going to take the limit as x goes to 0 of 1 over the square root of x plus 1 plus 1. And when I plug in 0 for x, well, the top is 1, of course. The denominator, that would be 0 plus 1, which is 1. The square root of 1 is 1, and 1 plus 1 is 2. So my answer is 1 over 2. So, not so bad, but you may have not been familiar with this method of attack when we want to rationalize part of our function. And so now you're familiar with it. You can add that to your arsenal, and another technique you can utilize to solve different limits. Let's go ahead and look at another example. The next example will be similar to this, and then the following examples will be different in their own way. All right, so here we're finding the limit as x goes to 4 of the square root of x plus 5 minus 3 over x minus 4. I will plug in 4 for x. 4 plus 5 is 9. Square root of 9 is 3. 3 minus 3 is 0. 4 minus 4 is 0. I get 0 over 0 in determinate form. There is hope. What should I do? All right, so you've seen an example just like this, so you should be familiar with what to do. I would ask you to pause the video right now and try to work it out. When you unpause, you'll see me work it out. Okay, so hopefully you figured out that you should multiply the top and bottom by the square root of x plus 5 plus 3. Square root x plus 5 plus 3. Square root x plus 5 plus 3. In my numerator, I got that a squared minus b squared deal, so that's x plus 5 minus 9. Again, it's this guy squared. A squared minus B squared. So 3 squared is 9. My bottom, again, I see no reason to have to multiply this out. Now, again, it should also understand what's causing the problem in the original limit. The issue in the original limit is x minus 4. That's what's making my denominator 0. So that's kind of what I want to get rid of. So there would be no sense to distribute the x minus 4 when my whole goal in life is to cancel that out through algebra. So I'm going to leave the x minus 4 there. X minus 4 times the square root of x plus 5 plus 3. Okay, so if you look at the top very beautifully, isn't it wonderful the way this stuff works out? 5 minus 9 is negative 4. So at the top, we get x minus 4. Thank you. And our bottom, of course, is x minus 4 times the square root of x plus 5 plus 3. Okay, x minus 4 cancels. So that's 1 over the square root of x plus 5 plus 3. And from this point, we can just plug in 4 for x. And you can kind of see, so this will be 1 over 4 plus 5 is 9. Square root of 9 is 3. 3 plus 3 is 6. So 1 over 6. All right, that's the answer to that guy. So first two examples were quite similar. Our next examples, they will all be different in their own light and bring a certain spice and flavor to the party. All right, let's look at the next example. Okay, very nice. Very nice indeed. So this has nothing to do with rationalizing. I mean, look at it. You don't see any radicals there. So I'm going to attack this. In fact, I'm going to attack this with reckless abandon. But before I attack it, I want you to think about it. I'm very curious to see if you're able to solve this guy without watching me solve it. So, and let's do this for our remaining examples. Let's pause the video, and you're going to have to think, of course, because you probably never did a limit like this. So let's pause the video and see if you can figure out a way to solve it. Okay, so I hope some of you were successful. The key is you know enough math now, and if you notice, like this math we're doing, and this type of math is probably the biggest issue calculus students have in AP Calculus in high school and in calculus in college. The math we're doing here to solve these problems is algebra. All this is we're doing is basic algebra. So all that's involved here, none of these things I'm doing are calculus techniques. These are algebra techniques. So you've covered enough algebra in Algebra 1 and Algebra 2 in pre-cal, so you got to kind of think about all that stuff. I'm sorry, it's unfortunate, but we're asking you to remember all of that stuff in order to solve these type of problems, and that's going to be the requirement for the rest of your mathematical careers. So, and I will say, you know, for a lot of these problems, there's more than one way to solve the problem. So some of you may have successfully solved this problem. So if we have the same answer, we're good, but our limits could be, not our limits, our methods could be different, and that's fine. And in fact, if you have a different method of solving this than the one I use, please share it with me. It may be better than my method, who knows? All right, so what I like to do when I have a fraction within a fraction, I should say this, when I have a sum or a difference of fractions within a fraction, I like to combine them and make them one fraction. And the way I do that is I multiply both these guys by the least common multiple of each denominator, which in this case would be 3 plus x times 3. So I'm gonna multiply both of these guys by 3 plus x times 3. So, and I'll explain fuller why I'm doing this. So I'm gonna multiply times 3 plus x times 3 on the top, 3 plus x times 3 on the bottom. The reason I'm doing this is this number will get rid of my denominator on each of these fractions. So when you multiply by the least common multiple of your denominators, that's the same thing as the least common denominator. What it does is it'll cancel out your denominators, and so you don't have to worry about those denominators anymore. So what happens, so I'm going to multiply this guy by this. What happens, of course, 3 plus x cancels, and I'm just left with 3. And 3 times 1, of course, is 3. Minus, now on this side, let me point this out because this is a misconception some have. Something, because I multiplied this by this guy and the 3 plus x canceled, that it remains canceled when I multiply by 1/3. Not true. This whole expression is being multiplied by this guy, and this whole expression is being multiplied by this guy. So when I get to multiply by this guy, I'm using the whole expression again. So the 3 plus x is still there. So now when I multiply by the 1/3, the 3 would cancel, and I'll be left with 3 plus x. Now notice there's a minus sign here that's critically important. So I'm going to put the 3 plus x in parentheses. So anytime you have any type of expression that's more than one term following a minus sign, put that in parentheses, because what that means is the minus sign applies to everything after. And a very common mistake would be to only apply it to the 3 and not the x. Okay, so that's what's happening in the numerator. The denominator would just be x times 3 plus x times 3. Again, we should understand what's causing the problem. I didn't even do this. I'm sorry. I forgot to plug in 0 for x in the very beginning. Please forgive me. If I plug in 0 for x, that would be 1/3 minus 1/3, which is 0. And of course, 0 on the bottom is 0. Now, what's causing the problem in my denominator, of course, is this x. So my hope is that I can get rid of this x, and then I can just plug in 0. So if you look at what's going to happen at the top, I'm going to write this negative sign distributed out so there's no confusion. So this will be 3 minus x on the top. Denominator is the same. X, 3 plus x, 3. So you'll see here the 3's will cancel. So negative x over x times 3 plus x times 3. And so at this point, I think since I haven't canceled the x yet. Let me not write limit yet. I've canceled x. I'm getting a little ahead of myself. So at this point, the x can cancel. He's gone. Now remember, when he cancels and there's nothing else there, you're left with a 1. So this is negative 1 over 3 plus x times 3. And I'm going to take the limit of this guy as x goes to 0. All right, so see what we get when we plug in 0 for x. So that would be 3 times 3, that's 9. So we get negative 1 over 9. Beautiful. So if you came up with negative 1 over 9, use a method different than mine. It's probably a good method. Again, if you had a different one, just let me know about it. And I do need to check the veracity of the method. You could have got lucky, but if you got the same answer as me, using a different method, you probably did a good method. If you got an answer the same as me and you did the same method I did, that's great as well. Let's move on to our next example. Okay, this one is actually pretty simple, but there's just a small part of it that some people miss. So there's a little speck of algebra in here that some people miss. I want to make sure that's understood. It's the only reason I did this one. So this one is really not that hard of a limit. So, okay, so I plug in 5 for x, 0 over 0. You see it, correct? So the factoring here is pretty basic, right? So you have 5 minus x over x plus 5 times x minus 5. And what I need, the only thing I'm using this example for is to point out the relationship between these two. Now, when you have a binomial, 2 terms, and they're in different order with different signs, what I mean is they're in different order, and this x is negative and that x is positive, and this 5 is positive and that 5 is negative. So in different order with opposite signs, that means they have a difference of negative 1. So 5 minus x divided by x minus 5 is going to give me negative 1. Now, if that's what I said is hard to picture, then you can think of it like this. Let's say I factor out -1 from this term. So I'm factoring out a -1. So I'm dividing each of these terms by -1. Well, if I divide -x by -1, I'll get x. And if I divide 5 by -1, I'll get -5. So you can think of it like that as well if you want to. X plus 5, x minus 5. But either way you look at it, this is going to cancel and you're going to be left with -1 on the top. So this is -1 over x plus 5. And what are we doing? The limit as x goes to 5. And so that's -1 over 10. So again, just understanding that this guy divided by that guy is -1. It's really the only reason I use this pretty simple example. Okay, I apologize for the simplicity of this guy. Let's see what the next example is. Hopefully it's a little more spicy. Man, pretty spicy. All right. So this one, okay, I'm sorry, let me go through the process. I get ahead of myself sometimes. If I plug in 16 for x, the square root of 16 is 4, 4 minus 4 is 0, 16 minus 16 is 0, I get 0 over 0, indeterminate form. There's hope. Let's see what we can do. So in this problem, it may not be that obvious, but you can factor your denominator. Like this guy can be factored. And this is the difference of squares. Actually, this guy, believe it or not, can be factored the same way you factored this. So let's talk about the difference of squares, because I did difference of squares here. Difference of square means I have a square and they're being subtracted. Squares, difference of squares. So when I have the difference of squares, what I can do is take the square root of both these numbers. This is x, this is 5, and do 1 plus 1 minus, x plus 5, x minus 5. Because it's based off, what we had to use earlier, this particular phenomenon. So if I have a difference of squares, it's going to be the square root of these two guys, 1 plus 1 minus. All this stuff comes together like spaghetti and mozzarella sauce. Not mozzarella sauce, marinara sauce. All right, anyway. So I submit to you today that this guy could be factored difference of squares. You may say, well, I see 16 is something squared, but x is not. And I would disagree with you. X is something squared. X is the square root of x squared. So 4 minus the square root of x. So my denominator can be written as x plus, I feel like I need a new sheet of paper. That just looks, pardon that. Let me write the numerator again, 4 minus the square root of x. Let's restart. Now my denominator can be written as the square root of x plus 4 times the square root of x minus 4. And so hopefully you can see if you were to multiply that out, you would get x minus 16. Now notice we have the same deal I addressed in the previous problem. These are the same guys. They're in different order and different signs. So if I cancel these out, I'm going to get -1. So this is going to be -1. So these two canceled and gave me -1. So that's going to be -1 over the square root of x plus 4. Now I can plug in 16 for x. Square root of 16 is 16. The square root of 16 is 4. And 4 plus 4 is 8. So this is -1 over 8. All right. So yes, I can factor this guy. You may have never thought you could factor something like this, but yes, yes you can. Si se puede, porque no. All right, let's look at the next example. Ooh, spicy. All right, you can't even see it. All right, there we go. There's our next example. This is actually, now we're getting to the meat of this lesson. This is actually one of those special limits I talked about. So in the very beginning, I said there are going to be 2 special limits. One I'll do before we talk about Squeeze Theorem, and one I'll do after. This is one I'm going to do before we talk about Squeeze Theorem. So and I'm going to go and I'm going to do what I do. But I would like you to look at this this one yourself, I would be very proud if you're able to solve this guy based on what you know. Now, we're going to learn a little bit later. Once we go over derivatives, we're going to learn a very beneficial method of solving limits called L'Hopital's rule. This could be done with L'Hopital's very easily. So a little bit later, this is an easy limit to solve. You may say, well, why aren't we doing L'Hopital's rule now? Because to do L'Hopital's rule, you got to know derivatives. And some of you will say, well, we know derivatives. We did derivatives in pre-cal. Well, we haven't done derivatives to the extent in pre-cal that we need to do in order to start doing L'Hopital's rule. So we're going to wait until our derivative plate is full, and then we'll introduce L'Hopital's rule. But still, I can still do this without L'Hopital's rule. In fact, I have a couple of different ways I can do this particular limit. So I want you to think about it. This one will be a tough one for you to figure out, quite honestly. But we have covered stuff in pre-cal, and what we talked about today, that you should be able to solve this if you really think about it, but it's going to be tough. So still, even if you think you can't do it, I still want you to pause the video and try to think of a method to solve this one. You might surprise yourself. Never doubt yourself. Always believe in yourself. Always believe in your intellectual ability and potential to do great things. So pause the video, see what you can do to this problem. All right, so even if you were unable to figure out a way to solve this, I hope you gave it a good amount of time and really thought through some different things and just try some things and just to see what would happen. Okay, so what am I going to do? Now, just think of the things you could think about. Some of you may have thought, well, I can factor, and you can factor this. I'm not going to. I'm not going to do anything crazy like that. But you could factor this, and you could factor this as 1 minus the square root of cosine of x times 1 plus the square root of cosine of x. And did the same thing at the bottom. I'm thinking that process through. I don't see that really doing much. So that's not what I'm going to do. What I'm going to do is I'm going to steal a lot of this, believe it or not, a lot of this stuff. I'm looking for the paper. A lot of this is going to this phenomenon. So this is the phenomenon I'm going to use, even though there's no radicals here that I'm trying to rationalize. But actually what I'm trying to bring to the party are my trigonometric identities, particularly the Pythagorean identity. So that's what I'm trying to bring to the party. And if you recall, the Pythagorean identities dealt with the trig functions being squared. So it's very good to use here. So what I'm going to do is multiply the top and bottom by 1 plus cosine x. So 1 plus cosine x over 1 plus cosine x. And I'll remind you of those trigonometric identities. Well, right now, I'll remind you of the 3 Pythagorean trigonometric identities. But it would be good to study. They will come in hand here and there. All right, so let's see what happens. So I'm going to multiply the top out, and that's going to be 1 minus cosine squared x. The bottom, again, I see no reason to multiply the bottom out. This is x times 1 plus cosine of x. And I have to apologize again. I just went to doing the problem. I didn't plug the number in. It's bad on my part because I understand that all of these are going to give me 0 over 0. But you don't necessarily know that. So I should keep going through the process of plugging this number in first. And I apologize for not plugging it in. So if I plug in 0 for x here, cosine of 0 is 1. 1 minus 1 is 0, and that's over 0. So I get 0 over 0. So I should have did that first. Apologize for not doing so. All right. So right now what you see, and again, the whole problem with this guy is that you have this x down here. That's the issue with this guy, that you have this x down there. So what I can do is this 1 minus cosine squared x, that's the same as sine x. Sine squared x, excuse me. So this is sine squared x over x times 1 plus cosine x. Now, I still haven't gotten rid of this x yet, correct? Okay, so what I can do now is I can turn this into a product of 2 functions. one function would be sine x over x. The other function, so I took one of these sine x's from the sine squared x. I took one of them. So I still have one left. So the other function will be sine x over x times 1 plus cosine. Excuse me, not x. I used the x over here. So just sine x over 1 plus cosine x. So this is limit of a product, taking a limit as x goes to 0. So you might say, man, that's still crazy. Yeah, you're probably right. But let's look at this. I don't want to look at this one yet, because I'm going to address this one in great detail. I want to look at this one for right now. So let's see. Now remember, if I take the limit of a product, it's just a product of the limit. So if I can take the limit of each of these individually and just multiply those answers by each other. If I take this limit, I will be plugging in 0 for x. Sine of 0 is 0, and cosine of 0 is 1. So if I plugged in 0 for x, I would get 0 over 2, which is 0. That's a good number. Again, 0 in your numerator is fine. You just get 0. So I would get 0 in this would equal 0, correct? Now, let's just say, hypothetically speaking, that the limit as x goes to 0 of sine x over x exists. Let's just say that. You don't know that right now, and we're going to address it. I promise. My next example is we're doing the limit of x goes to 0, sine x over x. I'm going to get it. I'm going to use Squeeze Theorem to get this particular limit. So trust me, the limit exists. So if this limit exists, whatever the number is, it's being multiplied by 0, correct? Because this limit is 0. Again, why is it 0? Because if I plug in 0 for x here, I would get sine of 0, which is 0, and I would get 1 plus the cosine of 0. The cosine of 0 is 1, so that would be 0 over 2 from 1 plus 1, and 0 over 2 is 0. So 0 times whatever number this is going to be 0. So this limit is 0. So it's pretty important to point out that I'm going to write it on this sheet, and I'm going to put it on the screen in a moment, but I want to give it its just due while it's here. It's pretty important to understand it. And this is one of my two special limits, that the limit as x goes to 0 of 1 minus cosine x over x is 0. That's important. That's one of two special limits. All right, so what's the other special limit? Well, we just been looking at it. It's the sine of x over x. The limit as x goes to 0 of the sine of x over x. All right. Now, you can see it in this first problem, this last problem we did, I should say, rather. You could see a little glimmer of hope that you could mess with this. If you look at this, like, you probably don't see anything you can do. And you're probably right. So to solve this, I'm going to use something called the Squeeze Theorem. So let me show you the Squeeze Theorem, talk about it a little bit, and then we'll use it to find this guy. Okay, this is the Squeeze Theorem. Again, in some books, it may be called the Sandwich Theorem or the Pinch Theorem, and you'll understand why once we look at it. So we have H, F, and G, their functions C and L are real numbers. So if H of x is less than or equal to F of x, which is less than or equal to G of x. Now let's talk about what that statement means. So this statement basically means that F is between H and G. That's what that means. F is greater than H or above H from a graphical standpoint, greater than or equal to H, I should say, or above or touching H from a graphical standpoint, and less than or equal to G, so below or touching G from a graphical standpoint. So basically it's in between, F is in between H and G. It's being squeezed between those two, or sandwiched between those two functions. So if F is between H and G for all x in an open interval containing C, except possibly at x equals C. And the reason this statement is in here, except possibly at x equals C, because it's a very good chance that f is not going to be defined at x equals c. It's a very good chance of that happening. So that's why that statement is there. So if f is between h and g for all x in the open interval containing c, except possibly at x equals c, and the limit as x goes to c of h is equal to the limit as x goes to c of g, which is L, then the limit of f of x as x goes to c is L. So what this guy is saying, if I have a function sandwiched between two other functions, so it's between these two guys, and if those two outside functions, if their limit at c is equal, so these are the outside functions. This is like the bread of the sandwich. F is the meat. So if the limit of the two outside guys is equal, then the limit of the function in the middle has to be the same thing. Has to be. And I'll show you from a graphical standpoint on this very example of sine x over x, why that has to work. So you may say, okay, maybe I kind of understand what that's saying. How in the world is that going to help me find the limit as x goes to 0 of sine of x over x? Well, let me show you. So these squeeze theorem problems, they can get pretty intricate. Because basically, if you have to use the squeeze theorem for a problem, that means you don't know how to find the limit of the problem. Like you're going deep into your well when you have to use the squeeze theorem. So to be able to find this limit with the squeeze theorem, this has to be the function in the middle. So the hardest type of problem would be you kind of figure out two functions where this function is squeezed between the two. And if you can't find the limit of this function already, it means you probably don't know how the graph looks. So it would be very difficult, extremely difficult to find two functions that you know that this function would be squeezed between. That would be very hard to figure out. So in a lot of cases, they give you the two functions that the function comes between. So let's say I give you two functions. So let's say, and for the sake of having some notation, let's say f of x is sine of x over x. And let's say another function, h of x equals 1. And let's say another function, let's call it g. Let's say g of x equals cosine x. All right, let's say we have those two statements. And so let's say I gave you this information, and I also told you that g is less than or equal to f, which is less than or equal to h. So let's say I told you this. Now, anytime you're trying to find the limit, and it's a hard limit, like this, man, I don't know what to do. Anytime you're trying to find a limit and it's a hard limit, and they give you something like this, you should be thinking squeeze theorem all day. Now, squeeze theorem may not apply, but if they give you something like this, you should always think squeeze theorem. So I already know the function is squeezed in between these two functions. But the second part is I have to show or find out that the limit of these two functions as x goes to 0 or whatever x is going to for the particular problem, they have to be the same. So let's take a look at it. So let's look at h. So the limit as x goes to 0 of h of x, well, h of x is just a constant. So the limit is going to be 1. The limit of a constant is that constant. Well, let's look at g. So the limit as x goes to 0 of g of x. So it's a trigonometric function. That's a well-behaved function. Again, polynomial and trigonometric functions, we can do direct substitution. So I'm just going to plug in 0 for x, and cosine of 0 is 1. So these two outside guys have the same limit. So since the limit of these two outside functions is 1, and this guy is squeezed between the two, then the limit of this guy as x goes to 0 has to be 1. So the limit of that guy is 1. So again, most problems you're going to see, they're going to give you two functions where the function that you're trying to find is between, because it's tremendously difficult, especially on this level being a first year calculus student, to try to figure out, not knowing what the graph of this function is, try to figure out two functions that will go on the outside of this function and also have equal limits as x goes to that number. That's tremendously difficult to be able to do as a first year calculus students. So generally they're gonna give you this bit of information, and you just need to check if the squeeze theorem applies. Normally on a problem like this, if the squeeze theorem applies, that's going to be the answer. If the squeeze theorem doesn't apply, one of your answer choice will say something like not enough information to find the limit, because based on what you know, you wouldn't have enough information to find the limit. So anyway, so the limit of the limit as x goes to 0 of sine x over x is 1. And just show you a graphical representation and further explain the squeeze theorem from a graphical standpoint. So I graphed these three functions I've used here in Desmos. So let's look at those graphs. So here is the graph, and you can see green is the function f of x equals 1. Red is the function sine x over x, and the blue is cosine of x. And so just to understand what the theorem is saying, so it's saying in some open interval, so it doesn't have to be from negative infinity to infinity, but in some interval, we can just take an interval here. And in fact, the smaller the interval, the better. So some interval that includes c. So in this little interval here, that includes 0, but not necessarily at 0. Why? Because sine of x over x is undefined at 0. So that's why it says maybe not right at 0. So in this little interval here, if you look at it, you can see that this red graph is squeezed between the green and the blue, sandwiched in or pinched in by those two functions. And again, you see they all meet right here when x is 0. And so that's why the limit as x goes to 0 of both these two guys, the outside functions, were 1. And so just think about it. If this function is squeezed between these two in an interval containing c, here's my c here, in this case it's 0, and their two limits are the same at that x value, then the inside function has to be the same. Again, remember, it's squeezed in between the two. So if those two outside functions have the same limit, the function in the middle has to have the same limit. So that's the rationale behind the squeeze theorem. And since we found our second special function, I just want to highlight the two special limits that we want to remember. So there they are. So those two are our two special limits. They are so special. So this is something you want to study and memorize. You don't want to work these limits out. So these are limits you want to study and memorize. We're going to utilize these a little bit later when we're doing derivatives, but we're also going to utilize them for other stuff. They're going to be quite beneficial for a number of things. So please remember that the limit as x goes to 0 of sine of x over x is 1, and the limit as x goes to 0 of 1 minus cosine of x over x is 0. Study those guys every day until you know them like you know the palm of your hand. Okay, so we went over the squeeze theorem. I'm going to do another squeeze theorem example real quick, and then I'll end the day with just a few remaining harder limits. All right, so here's a problem I would like to attack. So this problem says if g of x is 4 minus x squared and h of x is 4 plus x squared, and f is between g and h. So it's not even telling me what f is, but it is telling me that f is between g and h. What is the limit as x goes to 0 of f? Again, when I see this, I'm finding the limit of a function. I don't even know what the function is, but I know it's squeezed between these two functions. I should be thinking squeeze theorem. So I just need to see if the limit of these two functions as x goes to 0 is the same. If so, then that's going to obviously be the limit of f. So these are polynomial functions, well behaved. I can just plug in 0 for x. I can do direct substitution to find their limits. So if I plug in 0 into g, I'll get 4. And if I plug in 0 into h, I also get 4. So then that means that the limit of f as x goes to 0 must be 4. So you can see the type of way you're going to see Squeeze theorem. You'll see this provision. Now you have to remember it. So there's going to be a million things why it's very important to study, because you're going to see so many things. You might start confusing this thing with maybe something we call IVT, intermediate value theorem, and different stuff. So it's just important to study so you can distinguish between a lot of things. Now you don't have a lot to compare this to. So now every time you see this situation, you know to think Squeeze theorem, but you have to study so when more things come up that you still understand that such a problem is Squeeze theorem. Okay, so let's close out the lesson with a few remaining harder limits. All right, so let me just see how many I have here. 1, 2. Oh, I just have two remaining. Okay. So now we're going to use everything at our disposal that we've learned today, and algebra tricks we learned in previous classes to find these limits. So this is the limit as theta goes to 0 of tan theta over theta. So you know what I want you to do, and I want you to do it with integrity. I want you to give a sincere effort. Let your brain work a little bit. I want you to pause the video and think of if you can figure out how to solve this particular limit. Okay, so you may have been successful, you may have been unsuccessful, but if you at least attempted and tried and gave a very sincere effort to try to figure this out and use that brain power, even that brain power in a failure is going to be beneficial. Trust me. So to not pause the video and say, oh, he's going to explain it, I'm just going to watch it. That's not going to be as beneficial as you trying to think through and figure out these type of guys yourself. All right, so what can I do to this guy? Well, I know that I know that tan theta is sine over cosine. So why not rewrite that? Because I have a little understanding of how to find limits with sine and cosine a little bit. So I'm going to write tan theta as sine theta over cosine theta, and all that is over theta, right? Now, and this is also something, a little trick, I guess it's algebra, maybe it's arithmetic. So whenever you have a fraction divided by something, what it's being divided by, you can just put in your denominator. And I said political cause, political season. But anyway, so what's in my denominator? What I'm dividing by, I can just put in my denominator. So this is the same as sine theta over theta times cosine theta. So that's something you can always do. If you don't understand why I can do that, then you should understand when you divide, you multiply by the reciprocal. So you can think of this as sine theta over cosine theta times 1 over theta. Again, when you divide, you multiply by the reciprocal. The reciprocal of theta is 1 over theta. And so there you can see how you get theta times cosine. So just in general, if I have a fraction divided by something, I can put that something in the denominator of that fraction. Perfectly legal. Okay, so that was nice. Still, again, what's causing the problem in this, I didn't plug in 0 for, I apologize. I didn't go through my normal steps. I'm skipping things and I shouldn't do that. So I should have tried to plug in 0 for this function. So the tan of 0 is 0, and of course that would be 0. So 0 over 0. So what's causing the problem is this theta down here. So the theta is still there, and hopefully you understand that you can't cancel this theta with that theta. This theta is forever entangled. I shouldn't say entangled. This theta is forever connected to this sine, so they don't cancel. You can't just have a blank sine out there with no angle. You take sine, cosine, and tangent of angle, so there always has to be some angle there. So you can't get rid of that. So no way is that going away. So you can't cancel those. So please don't think that. But what I can do, because I should notice, hey, I got a sine theta here and a theta down there. I know how to do the limit of sine theta over theta. Why not rewrite this as the product of two limits? So why not write this as sine of theta over theta times, so I use sine theta and theta. Only thing that's left is cosine theta at the bottom. So times 1 over cosine theta. See your properties of limits coming in to help you. And we're taking the limit as x goes to 0.